Our universe has a birthday we all know about. The Big Bang marks that moment of explosive creation nearly 14 billion years ago. But that story is incomplete. It tells us what happened after the beginning, not what started it all. This leaves us with the greatest mystery in all of science. What, if anything, existed before the Big Bang? This is not just a philosophical puzzle. It is a fierce scientific race, a hunt for clues written in the fabric of space-time itself. By the end of this exploration, you will understand the frontier theories and the real evidence that could rewrite our cosmic origin story. We are going to confront the wall where our physics breaks down, meet the bizarre contenders for a pre-Big Bang reality, and learn how scientists are searching for ancient fossils in the sky. Could our universe be one bounce in an endless cycle, or just one bubble in an infinite multiverse? What do you believe lies on the other side of the beginning to find that starting line? We first have to understand the finish line of our current cosmic story. For decades, the most successful framework for describing the universe has been the ΛCDM model, often called the Standard Model of Cosmology. Its predictions are stunningly accurate, matching the glow of the cosmic microwave background, the distribution of galaxies, and the accelerating expansion driven by dark energy. This model gives us a powerful, mathematically elegant movie of cosmic evolution. But when we run that movie in reverse, rewinding the expansion of everything we see, the story takes a sharp turn into the unknown. All the galaxies, stars, and even space itself crunches down, getting hotter and denser with every step backward. The equations point relentlessly toward a single, unavoidable moment. A state of infinite density, infinite temperature, and zero volume. This is the initial singularity, the official mathematical starting point of the Big Bang. It is crucial to understand what this singularity represents. It is not a tiny, ultra-dense ball of matter floating somewhere in a pre-existing void. It is the point where space and time themselves are born. There is no outside, no before in the framework of our current physics, because time as we know it begins at that instant. This is where our greatest scientific triumph hits a wall. At the singularity, the very equations of Einstein's general relativity, which so beautifully describe the curvature of space-time by mass and energy, produce infinities. They break down completely. It is the equivalent of a calculator displaying error when you ask it to divide by zero. The singularity is not just a physical state we do not understand. It is a profound signal that our description of reality is incomplete. It acts as a veil, a cosmic curtain drawn across the very first moment, hiding any potential before from the view of our established science. So the race to understand what came before the Big Bang is, at its heart, a race to find the new physics that can lift that veil. This is where the mystery becomes a trap for our own language. We instinctively frame the question in terms of time. What came before the event? But if the Big Bang truly marks the origin of time itself, then asking what happened before it is like asking what lies north of the North Pole. On the surface, it seems like a perfectly reasonable geographical question. You can point a compass north and keep traveling. But once you reach that exact point, the very concept of north loses its meaning. Every single direction you can possibly face from the North Pole points south. The framework of north and south breaks down at that singular location. In the same way, our everyday concept of before and after is woven into the fabric of time. If time begins at the Big Bang singularity, then there is no temporal framework in which a before can exist. The question, as we normally mean it, might be meaningless within the rules of our current universe. So the real scientific pursuit is not about finding a calendar entry for a day that came before day one. It is far more profound. It is about searching for a deeper, more complete framework of reality, one where our familiar space and time are not the foundational stage, but rather actors that emerge from something else. Scientists are not looking for a literal yesterday. They are hunting for the parent theory, the cosmic context from which our universe of space and time could be born. This shifts the entire investigation. We are no longer rewinding a movie. We are trying to find the studio that produced the film, the physics that wrote the script for the Big Bang itself. The goal is to peer behind the veil of the initial singularity not with a clock, but with a new set of cosmic laws. This transforms a simple historical question into a revolutionary probe into the very nature of existence. Yet within that breakdown of our known physics lies a possible first clue. It comes from a profound refinement of the Big Bang story, a concept called cosmic inflation. Think of the classic Big Bang model as a simple, powerful sketch of cosmic history. Inflation is the detailed, high-resolution rendering that fills in the crucial first brushstrokes. It proposes that in the very first sliver of a second, far less than a trillionth of a second after the singularity, the infant universe did not expand at a steady pace. Instead, it underwent a burst of exponentially rapid expansion, inflating from a subatomic speck to something perhaps the size of a grapefruit in an unimaginably short time. This is not like a balloon being gently blown up. This is like that balloon inflating to the size of our observable universe in less time than it takes light to cross a single proton. This wild idea was not invented just for the sake of wonder. It was proposed to solve two major puzzles that the standard Big Bang model left glaringly unanswered. The first is the horizon problem. When we look at the cosmic microwave background, the ancient afterglow from when the universe became transparent, we see it is almost perfectly uniform in temperature in every direction we look. But in the standard model, there simply has not been enough time since the beginning for light, or heat, or any influence to travel across the vast distances to smooth everything out. It is as if you walked into a room and found 2 cups of coffee on opposite sides, both at exactly 85 degrees, but no one had ever been in the room to mix them. Inflation solves this by suggesting that everything we see in our observable universe was once crammed into an incredibly tiny, intimately connected region. That region was then stretched to cosmic size in an instant, preserving that initial uniformity. The second puzzle is the flatness problem. Our universe appears to be geometrically flat, meaning the fabric of space-time on large scales is not curved like a sphere or a saddle. For this to be true today, the density of the early universe had to be fine-tuned to an astonishingly precise value at the moment of the Big Bang. Inflation naturally produces this flatness, much like how blowing up a balloon makes a small patch on its surface appear flatter and flatter. So inflation is a brilliant theoretical patch, solving major issues and making stunning predictions that later observations confirmed. But here is the crucial and often overlooked twist in this story. While inflation happens immediately after the Planck time, the earliest moment we can currently describe, it acts like a cosmic reset button. That ferocious stretching of space-time would have smoothed out any wrinkles, any fossils, any potential fingerprints of whatever might have existed before inflation began. It erases the tape. This means that even if we one day develop a theory that describes a pre-Big Bang state, the period of inflation that followed may have wiped the slate so clean that all direct observational evidence of that prior era is forever lost to us. So inflation, our first great leap beyond the simple singularity, becomes a double-edged sword. It provides a more complete picture of the universe's first moments, yet it also raises a formidable new barrier in our race to see beyond them. If the veil of the singularity was not enough, inflation may have ironed that veil perfectly smooth, leaving us to wonder if we can ever find a thread to pull. But if inflation erases the past, where could we possibly look for an older cosmic signature? The answer forces us to confront the deepest rift in modern physics. To peer into that first flicker of existence, the Planck epoch lasting just 10 to the negative 43 seconds, we must understand gravity when the universe was smaller than a subatomic particle. This is a realm where our two most successful scientific theories stare at each other across an unbridgeable chasm. On one side stands general relativity, Einstein's masterpiece. It paints a breathtaking picture of the cosmos on the grandest scales, where gravity is not a force but the graceful curvature of space, time itself by mass and energy. It explains black holes, the bending of light, and the expansion of the universe with stunning precision. On the other side is quantum mechanics, the rulebook for the impossibly small. It governs the chaotic, probabilistic dance of particles and forces, where things can be in two places at once and pop in and out of existence seemingly at random. It underpins every microchip, every laser, and the very structure of atoms. Both theories are magnificently accurate within their own domains, but they speak entirely different languages. General relativity is smooth, deterministic, and geometric. Quantum mechanics is jittery, probabilistic, and discrete. When you try to merge them, to ask what happens to gravity at the scale of a single quantum particle, the mathematics explodes into nonsense. Infinities appear and the equations lose all predictive power. This is not a minor technical issue. It is a fundamental crisis. The initial singularity of the Big Bang is precisely the point where the domain of general relativity, the extremely massive and dense, collides with the domain of quantum mechanics, the extremely small. To remove that singularity, to see if something could have preceded it, we need a theory that does not break down there. We need a theory of quantum gravity, a single set of rules that can describe how space-time itself behaves when it is crumpled into a quantum scale knot. Therefore, the race to understand what happened before the Big Bang is not merely an archaeological dig into cosmic history. It is the forefront of theoretical physics, a desperate and thrilling sprint to unify our understanding of reality. Whoever finds this unified theory will not just get a Nobel Prize. They might get the first glimpse behind the ultimate cosmic curtain. The search for quantum gravity is not a single path, but a branching network of possibilities, each offering a different doorway through the singularity. One of the most ancient and enduring ideas for what lies on the other side is the concept of a universe with no beginning and no end, only an endless rhythm of death and rebirth. This is the cyclic universe, a model that transforms the Big Bang from a unique creation event into a recurring phase in an eternal cosmic cycle. The appeal is deeply intuitive. It replaces a singular, inexplicable beginning with a process that feels more natural, like the turning of seasons or the inhale and exhale of a breath. In this view, our expanding universe is not the first chapter, but merely the latest in an infinite series. The classic version of this story involves a big crunch. Imagine the current expansion of everything eventually slowing, halting, and then reversing. Galaxies would rush together, space would contract, and all matter and energy would be compressed back into an ultra-hot, ultra-dense state remarkably similar to the Big Bang's initial conditions. This collapse would not end in a meaningless singularity, according to the cyclic idea, but would instead act as a cosmic reset, rebounding into a new expansion, a new universe born from the ashes of the old. This elegant vision, however, runs into serious problems with our modern understanding of dark energy. Observations show the universe's expansion is not slowing down, it is accelerating. A mysterious repulsive force, dark energy, seems to be winning, making a future where everything gravitationally pulls back together seem less and less likely. So how could a cycle persist? This is where a modern, sophisticated revival of the cyclic concept enters the race, a model known as the Ekpyrotic universe. Its name comes from the Greek word for conflagration or out of fire, but the mechanism it proposes is far more geometric and startling. The Ekpyrotic model is built upon the framework of string theory, which suggests the fundamental ingredients of reality are not point-like particles, but tiny, vibrating strings. One consequence of this theory is the possibility of extra dimensions of space, curled up so small we never perceive them. Within this landscape, our entire three-dimensional universe could be just one surface, or brane, floating within a higher dimensional expanse. Picture our cosmos as a vast, flat sheet of paper adrift in a silent, unseen ocean. Now imagine another such sheet, another three-dimensional brane, floating parallel to ours in that higher dimensional sea. The Ekpyrotic scenario proposes that our Big Bang was not an explosion from a point, but the result of a collision between our brane and a neighboring one. This titanic, gentle smash in the higher dimensional bulk would have deposited an enormous amount of energy into our brane, heating it instantly and setting off the expansion and particle creation we see as the hot Big Bang. After the collision, the branes would bounce apart, with our universe expanding and cooling on its sheet, much as we observe. Eventually, the attraction between them would pull them together again, leading to another collision and another cosmic rebirth. This creates a cyclic model without a traditional big crunch, driven instead by a rhythmic dance of branes in a hidden dimensional arena. The appeal of this model is profound. It eliminates the need for a true beginning from nothing, offering instead an eternal, if violent, rhythm. It also makes a tantalizing prediction. Such a brane collision would not create the perfectly smooth, quantum-seeded fluctuations of inflation. Instead, it would generate distinct, non-random patterns or textures in the very early universe. These textures would leave a faint imprint on the cosmic microwave background, the universe's first light. This means the theory is, in principle, testable. We could look for specific, telltale signatures in that ancient afterglow. Cosmic bruises from the collision that started it all. The hunt for these signatures is ongoing, a meticulous search through the subtle temperature variations of the microwave sky. So far, the data from missions like the Planck satellite show a cosmos that looks incredibly smooth and consistent with the predictions of inflation, not with a brane collision. But the search continues, because finding even a hint of such a pattern would be a discovery of unimaginable scale. The first direct evidence that our universe is just one page in an infinite, colliding book. Yet another doorway through the singularity offers a vision even more radical than a brane collision. This contender asks us to picture a universe that never truly began, but instead, simply turned a corner. It is known as the bouncing universe model, and while it shares a family resemblance with the classic cyclic idea, its mechanism is born from the heart of quantum gravity itself. The difference is crucial. The old cyclic model relied on a big crunch, a total gravitational collapse into a singularity before a hypothetical rebound. The bouncing universe model proposes that a previous cosmic phase never reached that point of infinite density at all. Imagine the universe not as a balloon popping and reinflating, but as a cosmic spring. In this picture, our expanding universe was preceded by a long period of contraction. All the galaxies, space, and time of that prior era were slowly, inevitably, drawing together. But according to classical general relativity, that contraction would accelerate unchecked, culminating in a catastrophic singularity, the end of the line. The bounce model introduces a quantum correction. It suggests that as the universe compressed to an unimaginably small, but finite, size, somewhere near the Planck scale, the strange rules of quantum gravity would take over. At that extreme density, the fabric of space-time would no longer be smooth and continuous as Einstein described. It would become granular, foamy, and subject to intense quantum fluctuations. In this realm, a remarkable repulsive force could emerge from the quantum nature of geometry itself. This force would act like a perfect cosmic shock absorber. Just as a compressed spring reaches its limit and pushes back, the universe would hit a minimum size, and that quantum repulsion would become dominant, halting the collapse and reversing it into the expansion we see today. There was no moment of infinite density, no true singularity. There was only a transition, a cosmic bounce from contraction to expansion. This idea elegantly sidesteps the need for a beginning from nothing. It suggests an eternal, perhaps cyclical, timeline where phases of expansion and contraction follow one another, linked by these quantum bounces. Each cycle could be incredibly long, lasting trillions of years, with the bounce acting as a reset that produces a new hot, dense state, a new Big Bang from the ashes of the old. For this to work, however, Scientists must find a specific modification to Einstein's equations, one that becomes significant only at those insane densities and introduces the necessary repulsive quantum pressure. Several theories of quantum gravity, including loop quantum cosmology, a leading approach, naturally predict such a bounce. They replace the singular, infinitely dense point with a quantum bridge to a prior cosmic phase. The profound implication is that our entire cosmic history, from the first stars to the distant future, may be just one chapter in an endless book, with each chapter beginning not with a mysterious creation, but with a graceful, quantum-powered rebound. The universe forgets its previous contraction in the fiery heat of the bounce, yet carries forward some subtle quantum imprint. This leads to a haunting and beautiful question. If our universe is the child of a bounce, what faint memories might it carry from the universe that came before? But what if the universe did not bounce or collide? What if it simply stirred from an eternal slumber? This leads us to a third, profoundly different contender for our cosmic origin. It is the idea of an emergent universe, one that did not burst forth from a singularity, but transitioned gently from a timeless, static state that may have lasted forever. Picture not an explosion, but a quiet awakening. In this scenario, the cosmos begins not with a bang, but with a seed. Scientists sometimes call this the cosmic egg, but it is not an egg in the familiar sense. It is not something that existed in a pre-existing time, waiting to hatch. Instead, imagine a primordial state of reality, incredibly small, incredibly dense, and perfectly balanced. For an endless duration, this state just was. It was metastable, meaning it was in a kind of suspended animation, a precarious equilibrium that could, in theory, persist indefinitely. Within this static seed, the fabric of space-time itself was coiled and frozen. There was no expansion, no contraction, no flow of time as we experience it. It was a universe in waiting. Then, something tipped the balance, perhaps a random quantum fluctuation, the same kind of jitter that causes particles to pop in and out of existence in a vacuum, occurred within this dense core. In our expanding universe, such fluctuations are tiny and short-lived. But in that ultra-dense, primordial state, a single fluctuation could have been amplified catastrophically. It could have acted as the trigger, the single grain of sand that starts an avalanche, destabilizing the entire metastable configuration. That tiny quantum event would have initiated the expansion, unfurling space and time in a process that eventually became the hot, energetic universe of the Big Bang. The transition would have been swift, transforming that eternal, silent egg into the dynamic, expanding cosmos we inhabit. This framework elegantly sidesteps the philosophical thorn of a true beginning from absolute nothingness. There is no moment of creation ex nihilo. Instead, there is a transition from one form of existence timeless and static, to another, our familiar realm of flowing time and expanding space. The question of what happened before the Big Bang is reframed. In this model, asking what came before the transition is like asking what happened before the first note of a song that had been silently written for eternity. The sheet music existed, complete and whole, in a state of potential. The act of playing it brought it into our experience of sequence and time. The profound implication here is that time itself may be an emergent property, not a fundamental feature of reality. It is something that crystallized, that began to tick, only when the universe started its expansion. Before that transition, the concept of before and after may have had no meaning, because the stage on which those events play out did not yet exist. So the cosmic egg model offers a different kind of eternity, not an endless cycle of bangs and crunches, but an infinite past of poised potential, finally ignited by a random quantum spark. It suggests our universe's story is not one of birth from nothing, but of awakening from a dreamless sleep that had no beginning. There is another doorway, one that leads not to a prior cycle or a static seed, but to a reality of unimaginable vastness. This contender suggests our entire universe, with its one Big Bang and 14 billion years of history, is just a single bubble in an endless, frothing cosmic sea. This is the Multiverse Hypothesis, and it radically reframes our original question. Instead of asking what came before our Big Bang, we must ask what is happening outside of it, in a realm that operates by rules we can scarcely comprehend. The most compelling version of this idea emerges from the theory of cosmic inflation itself. Recall that brief, explosive stretching of space-time that solved the horizon and flatness problems. What if that process never truly stopped? The theory of eternal inflation proposes that the inflationary expansion is the default, stable state of a primordial, high-energy field. In this roiling, hyper-expanding quantum foam, random fluctuations can occasionally cause a tiny patch of this inflating space to drop into a lower energy state. When this happens, that patch stops inflating violently. The enormous energy locked in that field is released, instantly heating that region and creating a hot, dense soup of particles. In other words, that patch becomes a Big Bang, giving birth to a new, distinct universe like our own, which then expands and cools within its own bubble. Meanwhile, the surrounding inflating space continues to stretch at an incomprehensible rate, creating an ever-growing background in which new bubble universes are constantly nucleating forever. Our cosmos is just one bubble among an infinite, ever-increasing number, all causally disconnected from one another, each with its own potentially unique laws of physics. This leads to a second, parallel vision from the depths of string theory, known as the landscape. String theory, in its quest to unify all forces, suggests there may not be one unique set of fundamental constants and laws, but a staggering number of possible stable configurations, perhaps 10 to the 500 different versions. Each configuration represents a different possible vacuum state for a universe, with different strengths for gravity, different particle masses, and different outcomes. In the framework of eternal inflation, each bubble universe could settle into one of these countless possible vacuum states at random. In this landscape, our universe's particular laws, the charge of an electron, the strength of gravity, are not finely tuned miracles necessary for life. They are simply the local bylaws of our accidental bubble. Somewhere out there in the multiverse, other bubbles may have laws where atoms never form, or where gravity is so strong universes collapse instantly. Our bubble allowed for stars, planets, and us. So what does this mean for the moment before our Big Bang? In the multiverse framework, that moment is not a beginning of everything, but a local transition within an eternally existing, and perhaps infinitely old, meta-reality. The question of what happened before our Big Bang transforms into a question about the dynamics of this larger multiverse. Was there a first bubble, or has the process of eternal inflation or some other multiverse-generating mechanism simply been going on forever, with no ultimate beginning or end? The singularity that marks the start of our bubble's history is just a boundary from our perspective, a shoreline between our cosmic island and the wider ocean. The ocean itself may have no beginning we can point to. This idea is both liberating and profoundly disorienting. It suggests the ultimate answers we seek about our origin may lie not in the distant past of our universe, but in the uncharted geography of a reality so vast, our entire cosmos is but a speck within it. Yet there is a final, profoundly elegant contender that redefines the very meaning of a cycle. It comes from one of the most brilliant minds in physics, Roger Penrose, and his model is called Conformal Cyclic Cosmology. Its proposal is as beautiful as it is strange. Penrose suggests that the ultimate fate of our universe is not a dead, cold emptiness, but a gateway to a new beginning. In the far, far future, trillions upon trillions of years from now, all matter will have decayed. Black holes will have evaporated through Hawking radiation, and the cosmos will be an unimaginably vast, nearly empty sea of low-energy photons and gravitons, all stretched to immense wavelengths by the relentless expansion. In this state, the universe loses all sense of scale. There are no particles with mass, no rulers to measure distance, no clocks to tick off time. Everything is smooth, uniform radiation. Penrose realized that this distant future state has a remarkable mathematical property. Through a process called conformal rescaling, a kind of mathematical transformation that removes concepts of scale and distance, this endless, empty future can be mapped directly onto the hot, dense, ultra-smooth singularity of a new Big Bang. Think of it like this. Imagine a perfectly smooth, featureless desert that stretches to the horizon in every direction. Now, imagine a single, incredibly dense grain of sand. If you remove all notions of size and distance through a mathematical lens, those two landscapes, the infinite desert and the singular grain, become indistinguishable. They are conformally equivalent. In Penrose's vision, the cold, expanded eternity of one universe's end is not a wall. It is a seamless bridge to the hot, concentrated beginning of the next. There is no violent bounce, no brane collision, no mysterious quantum trigger. There is only a transformation of perspective, where the end of time in one epoch becomes the beginning of time in the next, in a cycle that has neither a true start nor a definitive finish. This is a cycle not of matter, but of geometry and information. The most provocative part of Penrose's theory is his claim to have found evidence. He argues that if a previous universe existed before ours, its most energetic events, like the collisions of supermassive black holes, would have sent powerful gravitational waves rippling through space-time. At the conformal boundary where that universe ended and ours began, those ripples could have imprinted faint, circular patterns on the cosmic microwave background, like echoes from a prior age. Penrose and his colleagues have published analyses claiming to detect these telltale circles in the CMB data, rings of slightly altered temperature that they call Hawking points. The scientific community's response has been intense skepticism. Many cosmologists argue these patterns are likely statistical flukes, consistent with the random noise expected in the CMB, and that the data from the Planck satellite does not support the claim. The controversy remains unresolved, a testament to how difficult it is to find a fingerprint from a universe that died before ours was born. Yet the idea stands as a breathtaking poetic vision. It suggests that creation is not a singular event in the distant past, but an eternal return, where each universe's quiet expiration is, from another viewpoint, a brilliant and fiery dawn. Amidst these grand cosmic cycles and collisions, a far more radical idea whispers from the edges of theoretical physics. It suggests our entire three-dimensional reality, with all its stars, planets, and people, might be a magnificent illusion, a cosmic projection. This is the holographic principle, and it could shatter our understanding of the Big Bang's beginning. The seed of this astonishing concept comes not from cosmology's first moments, but from the dark hearts of black holes. Physicists wrestling with black hole thermodynamics uncovered a profound paradox. A black hole's entropy, which is a measure of its hidden information or disorder, does not scale with its volume as you might expect. Instead, it scales with the surface area of its event horizon, the point of no return. It is as if all the information about everything that ever fell into the black hole is not lost within its infinite depth, but is somehow painted, pixel by pixel, onto its two-dimensional spherical surface. The three-dimensional interior is described completely by a two-dimensional boundary. This hinted at a rule that might apply to the universe itself. The holographic principle boldly proposes that all the information contained within any volume of space can be fully encoded on the lower dimensional boundary that surrounds it. Our rich, three-dimensional experience of reality, the feeling of depth, the solidity of objects, the vast distances between galaxies, could be a holographic projection from a vast, complex, two-dimensional surface at the edge of the cosmos. Now, apply this dizzying perspective to the very first moment. The initial singularity of the Big Bang represents a point of infinite density where our three-dimensional space-time collapses. But what if, from the holographic viewpoint, that catastrophic collapse is just a shadow on the wall? The true, fundamental description of the universe's birth might not be a story of an exploding point in three dimensions. It could be the story of information organizing itself on a two-dimensional surface, like a cosmic film reel. The Big Bang we think we know, with its expanding fireball in three spatial dimensions, would then be a projection, a translation of that deeper, simpler code into the immersive reality we inhabit. The terrifying singularity vanishes, replaced by a smooth transition in the information on that boundary surface. This reframes the question of what happened before the Big Bang in a way that makes our old language seem almost primitive. Asking what existed before our three-dimensional universe is like a character in a movie asking what happened before the first frame of the film. The answer does not lie within the movie's plot. It lies in the projector, in the reel of film itself, a reality of a different, simpler dimension. The before might be a configuration of information on that fundamental surface, a pattern that, when played, projects our entire cosmic history into being. In this view, time and space as we know them are not the stage but part of the show. They emerge from something more basic, a realm where concepts like where and when may have no inherent meaning. The hunt for a pre-Big Bang reality becomes a hunt for the projector and the film, a search for the timeless, spaceless code from which all of existence is rendered. It suggests that to understand our origin, we must look not inward to a point, but outward to a screen we have only just begun to imagine. Yet this search for a deeper reality must confront a more fundamental mystery than geometry or collisions, one written into the fabric of every moment we experience. It is the relentless, one-way flow of time itself. Why do we remember the past but not the future? Why does an egg scramble easily but never unscramble? This directionality, time's arrow, is not baked into the basic laws of physics, which work perfectly well running backward. Its origin points us to a single, startling fact about our universe's birth. The cosmos began in a state of incredibly low entropy. In simple terms, entropy is a measure of disorder or randomness. The second law of thermodynamics states that in any closed system, the total entropy always increases over time. This is why your room gets messy if you don't clean it, why ice melts in your drink, and why we grow older. It is the statistical tendency of things to move from order to disorder, from concentrated arrangements to scattered ones. That increasing entropy is what gives time its irreversible direction. The puzzle is the starting point. For entropy to increase for 14 billion years, giving us a clear arrow of time, it had to start from an extraordinarily low value. Think of a brand new deck of cards, perfectly ordered by suit and number. Shuffle it once and it becomes slightly disordered. Keep shuffling and it becomes completely random. Our universe is like that shuffled deck, constantly becoming more disordered. But the baffling part is that first, pristine, ordered deck. The Big Bang presented us with a universe that was hot and dense, yes, but also incredibly smooth and uniform, a state of remarkably low entropy. This is deeply counterintuitive. A hot, dense fireball sounds chaotic, but a truly high entropy state would have been a mess of black holes and random fluctuations from the very first instant. Instead, we got a smooth, ultra-organized starting point, a cosmic deck of cards perfectly stacked. This low entropy beginning is the ultimate wind-up toy. It has been winding down, creating structure and complexity like stars and life, ever since. But why was it wound up so tightly in the first place? This is not a minor detail. It is the foundational condition for everything that followed, including our own existence. Physicists like Roger Penrose have calculated that the odds of our universe popping into existence with such a specific, low entropy configuration are astronomically, almost impossibly small. It would be far more likely for a universe to begin in a maximum entropy state, a featureless, lifeless thermal equilibrium, a cosmic soup with no gradients, no structure, and no arrow of time. The fact that we are here, in a universe with a clear past and future, means something profoundly special happened at or before the beginning. This forces the question of what came before into a new dimension. We are no longer just looking for a geometric predecessor to the singularity. We are searching for a mechanism that could explain this incredibly fine-tuned, low-entropy initial condition. Did some prior process select for this specific, unlikely state? One compelling idea ties back to the multiverse. In an eternally inflating landscape, while countless bubble universes may form with random initial conditions, only those that begin with a low enough entropy could ever develop complexity, stars, planets, and observers. We find ourselves in such a universe not because it was likely, but because it was necessary for us to be here to ask the question. Other possibilities suggest that a prior contracting phase, like in a bouncing universe model, could naturally produce a low entropy boundary at the bounce through gravitational effects, effectively resetting the arrow of time for each new cycle. Or perhaps, as in Penrose's own conformal cyclic cosmology, the smooth, empty eternity of a previous universe's end provides that pristine, low-entropy starting point for the next. The quest to understand what happened before the Big Bang thus becomes, in part, a hunt for the origin of time's arrow. It asks what cosmic factory could have produced a universe so delicately poised between order and chaos, wound up and ready to run. The answer may lie not in a first cause, but in a statistical filter, a cyclic reset, or a selection principle woven into the fabric of a much larger reality. Theoretical doorways are breathtaking, but science demands evidence. The race now moves from the blackboard to the sky, becoming a form of cosmic archaeology. We are searching for fossils, not bones buried in rock, but ancient imprints pressed into the fabric of space-time itself, relics that could have survived from a reality that predates our own. Our most powerful tool in this dig is the oldest light in the universe, the cosmic microwave background. This faint, cold glow is the afterglow of the Big Bang, released when the hot, opaque plasma of the infant universe cooled enough to become transparent, about 380,000 years after the beginning. It is the ultimate baby picture, a snapshot of the cosmos in its infancy. But to a cosmologist, it is so much more than a simple photograph. It is a complex data stream, a cosmic message encoded in tiny variations of temperature and polarization. The patterns we see in this light are the seeds of all future structure. The slight over-densities that would, over billions of years, collapse under gravity to form galaxies and clusters. The prevailing theory of inflation predicts a very specific statistical signature for these fluctuations, a kind of cosmic fingerprint that has been overwhelmingly confirmed. Yet, if any of the pre-Big Bang models are correct, there is a slim chance they left a secondary imprint, a faint whisper beneath the primary signal. Imagine the CMB as a pristine, ancient canvas. The main painting was done by inflation, applying broad, predictable strokes. But if our universe emerged from a bounce, a collision, or a prior cycle, that violent transition might have scuffed the canvas or left a nearly invisible watermark before the painter even began. These would be primordial fossils, signals that do not fit the standard inflationary story. One potential fossil is a specific type of pattern in the polarization of the light. The CMB light can be polarized in two fundamental ways, called E modes and B modes. E modes are generally created by density fluctuations, the standard stuff of the early universe. But certain B modes, especially at large angular scales, could be generated by something far more exotic, primordial gravitational waves. These are not waves from colliding black holes, but ripples in space-time itself, stretched to cosmic scales by the universe's expansion. Inflation can produce them, but so could other dramatic events like a brane collision or a quantum bounce. Finding the specific signature of these primordial B modes would be like discovering a fossilized tremor from the universe's first split second, a direct probe of physics at energies we can never recreate. Another fossil could be statistical anomalies, subtle correlations or patterns in the temperature map that defy the random, Gaussian statistics predicted by simple inflation. For instance, some scientists have searched for evidence of concentric circles or other geometric shapes in the CMB. Potential bruises from a colliding brane universe or echoes from a previous cosmic cycle. Others look for evidence that our universe is not perfectly isotropic, that it has a preferred direction or axis imprinted from its birth in a larger, asymmetric meta-reality. The search is painstaking. It involves satellites like Planck and future observatories sifting through exquisitely precise maps of the sky, separating the faint cosmic signal from the foreground noise of our own galaxy and instrumental imperfections. It is a hunt for a whisper in a hurricane. So far, the CMB looks remarkably, almost disappointingly, consistent with the simplest models of inflation. No definitive evidence of colliding branes, no clear sign of a prior universe's gravitational waves, no obvious geometric scars. But the absence of evidence is not evidence of absence. We may simply not be looking with enough precision, or the fossils may be encoded in a way we have not yet learned to read. The cosmic canvas may be so clean because the pre-Big Bang era was completely erased, or because its signature is subtler than we ever imagined. This fossil hunt transforms the question from pure philosophy into an observational challenge. We are not just wondering what came before, we are building telescopes to look for its signature. The silence of the data so far is, itself, a profound piece of information, pushing theorists to refine their models and dream up new, testable predictions. The answer, if it exists, is written in that ancient light, waiting for us to learn its language. Buried within that ancient light could be the most direct message from creation's first instant. It is a signal known as primordial gravitational waves, and for cosmologists, they represent the ultimate prize, a potential whisper from the very edge of time. These are not the gravitational waves we detect today from colliding black holes or neutron stars. Those are like recent splashes in a cosmic pond. Primordial waves are something else entirely. They are the fossilized tremors from the universe's violent birth. Ripples in the very fabric of space-time that were generated in the first fraction of a second, and then stretched to unimaginably long wavelengths by the universe's subsequent expansion. If they exist, they are a direct probe of physics at energies we can never hope to recreate in a particle collider. Energies so high they approach the Planck scale, where gravity and quantum mechanics must unite. This makes them a possible bridge, a carrier of information from a realm that could predate our familiar Big Bang. The key to finding them lies not in their faint rumble, but in the unique mark they leave on the cosmic microwave background. When the universe was a searing plasma, these primordial ripples passing through would have gently shaken the soup of particles and light. This shaking imprinted a specific, swirly pattern on the polarization of the CMB light, a pattern known as primordial B modes. Think of the early universe as a windy pond. Density fluctuations from inflation create small, orderly waves on the surface, which correspond to the more common E-mode polarization. But a passing gravitational wave is like a stone dropped into that pond, creating a distinctive, swirling vortex in the water. That vortex is the B-mode signal. Detecting this specific swirl pattern in the polarization of the universe's first light would be like finding the fingerprint of the Big Bang's most energetic moments. The hunt for this signal is one of the most challenging endeavors in modern observational cosmology. The predicted signal is incredibly faint, buried beneath foreground emissions from our own galaxy's dust, and the subtle lensing effects of all the matter that has formed since. It is the equivalent of trying to hear a single, specific note played by a violin in a stadium during a thunderstorm while wearing earplugs. Initial excitement flared a decade ago when one experiment, BICEP-2, announced a possible detection. The scientific world held its breath. However, further analysis in collaboration with the Planck satellite revealed that the signal they saw was almost entirely due to cosmic dust within our Milky Way. A sobering lesson in the difficulty of the task. This setback did not end the search, it refined it. The quest for primordial B modes is now a primary driver for a new generation of ultra-sensitive observatories. Projects like the Simons Observatory in Chile and the proposed Lightbird satellite mission are being designed with unprecedented precision to map the CMB's polarization across the entire sky, meticulously separating the cosmic dust of our galaxy from the true cosmological signal. They are, in essence, building better ears to listen for that first note of creation. Finding it would be a discovery of Nobel Prize magnitude, not just confirming the details of cosmic inflation, but potentially opening a window to the physics of quantum gravity itself. It could tell us if the universe underwent a smooth, quantum-driven transition, or if its birth was marked by a more violent, collisional event. The continued silence, the absence of a definitive signal, is itself a powerful clue, already ruling out whole classes of inflationary models and pushing theorists toward new ideas. This quiet, persistent search for a swirl in ancient light is our best chance to touch the moment when everything began, to read a message sent directly from the other side of the singularity. While the cosmic microwave background is our most pristine ancient record, it is not the only place we might find a cosmic fossil. The search for a pre-Big Bang era extends into the very structure of the universe we see around us today, imprinted in the patterns of galaxies and the bedrock rules of physics itself. Consider the grand cosmic web, that vast, filamentary network of galaxies and clusters stretching across billions of light years. The specific way galaxies cluster together, their statistical distribution in space, is a direct descendant of those initial quantum seeds from the universe's infancy. Most models, including standard inflation, predict a particular pattern for this clustering, a specific mathematical signature. But what if we look closely and find a subtle deviation? A certain preferred scale, a strange correlation, or a pattern of voids and clusters that doesn't quite match the inflationary blueprint could be a monumental clue. It might suggest that the seeds for our cosmic structure were not sown by a brief period of smooth inflation alone, but were shaped or scarred by a dramatic event that preceded it. Imagine finding a unique grain in the wood of an ancient table. That grain could tell you about the environmental conditions the tree experienced long before it was ever cut down. Similarly, an anomaly in the galaxy distribution could be a fossilized imprint from the universe's very first moments, a structural memory of a brane collision, a quantum bounce, or some other pre-inflationary landscape. Beyond the architecture of space, we might find relics in the form of exotic particles predicted by theories of quantum gravity but never observed. One legendary example is the magnetic monopole. In our everyday experience, magnets always have two poles, a north and a south. You can cut a bar magnet in half, and you just get two smaller magnets, each with its own north and south. A magnetic monopole, however, would be a solitary north or south pole, a fundamental magnetic charge. Many grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces, predict that these bizarre entities should have been produced in colossal numbers in the extreme heat of the very early universe. Standard inflation provides an elegant solution to this monopole problem by diluting their density to essentially zero, explaining why we've never seen one. But what if we did? The detection of even a single, solitary magnetic monopole would be a cataclysmic event for physics. It would be direct evidence of those grand unified conditions, and it could imply that our inflationary period was not perfectly efficient, that a few of these primordial relics survived from an era before inflation smoothed everything away. Finding one would be like discovering a coin from a civilization thought to be completely erased by a flood. It is a tangible piece of a world that supposedly no longer exists. Perhaps the most profound fossils are not things we could hold but numbers. They are the fundamental constants of nature, the strength of gravity, the mass of an electron, the speed of light. Why do these numbers have the precise values they do? Their specific tuning allows for atoms, stars, and life. One haunting possibility is that these constants are not truly constant across all of reality, but only local bylaws in our cosmic bubble. In a multiverse scenario, each universe might have a random set of constants, but another, more testable idea is that these constants could vary very slightly over time or across space. If we found even a minuscule systematic change in, say, the fine structure constant, which governs the strength of electromagnetic interactions when looking in different directions or at different epochs, it would be revolutionary. Such a gradient could be a frozen shadow, a pointer indicating a direction or a center to the larger meta-reality from which our universe emerged. It would suggest our cosmos is not perfectly uniform all the way back to a singular point, but carries an imprint of asymmetry from its birth in a larger, structured environment. The silent, consistent hum of our physical laws is what we expect from a clean, isolated beginning. A faint, persistent drift in that hum would be the sound of something else, a whisper from beyond our inflationary bubble. The pursuit of these diverse fossils transforms cosmology into a forensic science. We are not just looking at the sky. We are sifting through the cosmic evidence for anything that breaks the mold, for any anomaly that the standard story cannot explain. Each deviation, each unexpected pattern or relic, is a potential crack in the wall of our current understanding. Through that crack, we might finally glimpse the contours of a reality that existed before time, space, and everything we know began its story. This relentless search for cosmic fossils runs headlong into a fundamental and sobering barrier. There is a wall in the sky we can never see past, a boundary set not by our technology, but by the laws of physics themselves. This is our cosmic event horizon. It defines the absolute limit of what we can ever observe, and it may forever lock away the answers we seek. The reason is deceptively simple: the finite speed of light. Light, the fastest messenger in the universe, takes time to travel. When we look at the sun, we see it as it was 8 minutes ago. When we gaze at the Andromeda galaxy, we see light that began its journey 2.5 million years in the past. This is a form of time travel, allowing us to peer into the universe's history. But we can only rewind the tape so far. Because the universe has a finite age, roughly 14 billion years, there is a maximum distance from which light has had time to reach us. We cannot see anything beyond that distance because its light simply hasn't arrived yet. That boundary is our observable universe. But here is where the plot thickens, and the horizon becomes an even more profound obstacle. During the period of cosmic inflation, space itself expanded faster than the speed of light. This means vast regions of the primordial universe were propelled so far apart, so quickly, that light signals from those regions could never cross the gulf to reach us, even given the entire age of the cosmos. They are forever beyond our causal reach. Think of it like two boats launched from the same dock onto an ocean that is stretching impossibly fast. Even if they shine their brightest lights directly at each other, the space between them grows so rapidly that the beams of light are carried backward, never making progress. Those boats, those regions of space, are lost to each other's view. This cosmic horizon creates a permanent veil. Any information about the state of the universe before or during inflation that resides in those now distant regions is, by definition, inaccessible to us. It is a part of cosmic history that has been carried over the horizon, like pages torn from the first chapter of a book and cast into a fire. This presents a profound philosophical challenge to our entire quest. If the most direct evidence for a pre-Big Bang state, be it a colliding brane, a quantum bounce, or a prior universe, exists only in those forever invisible regions, then our most elegant theories may be fundamentally untestable. Science thrives on observation and evidence, a beautiful mathematical model that explains everything but can never be checked against data, enters the realm of metaphysics, not empirical science. This forces us to confront a humbling possibility. The ultimate nature of our cosmic origin might lie permanently beyond the reach of scientific verification. We may be like detectives trying to solve a crime where all the physical evidence was destroyed before we arrived, leaving only logical deductions and philosophical arguments. Yet, this is not necessarily a counsel of despair. The cosmic horizon defines the limits of direct observation, but not the limits of inference. Scientists are masters of reading between the lines. We may never receive a light signal from a pre-inflationary era, but its influence might be encoded in the universal laws we can measure within our observable bubble. The specific, low entropy condition we started with, the precise values of the fundamental constants, the very existence of an arrow of time, these could all be indirect fossils, logical necessities imposed by the physics of a larger reality we cannot see. The horizon, therefore, reshapes the question. It asks us not just what came before, but whether the concept of before has any scientific meaning if its traces are forever exiled beyond the edge of sight. It challenges us to define what constitutes an answer. Is it a photograph from the other side, or is it a complete, self-consistent theory that explains every observable feature of our universe without needing that photograph? The silent void beyond the horizon may be the universe's way of telling us that some stories are written not in light, but in the indelible logic of existence itself. The cosmic horizon may set a limit on what we can see, but it cannot contain the reach of human curiosity. This brings us back to the heart of the theoretical battle, to the mathematicians and physicists who are not searching the sky for fossils, but are instead rebuilding the foundation of reality from the ground up. Their goal is not to find evidence of a prior era, but to construct a framework where the need for that singular, impossible starting point simply vanishes. They are trying to erase the error message from the calculator of the cosmos. To do this, they must confront the singularity head-on with a new kind of mathematics, one that can survive the extreme conditions of the universe's birth. The most promising weapons in this fight come from candidates for a theory of quantum gravity, approaches that treat the fabric of space-time not as a smooth, continuous stage, but as something built from discrete, quantized pieces. One of the leading contenders in this race is called loop quantum cosmology. It is a specific application of a broader theory known as loop quantum gravity. While the full theory aims to describe the quantum nature of space and time everywhere, loop quantum cosmology focuses that power on the universe as a whole, treating the entire cosmos as a single quantum system. The central idea is breathtaking in its simplicity and profound in its implications. In Einstein's general relativity, space-time is a smooth, malleable fabric. But at the tiniest possible scales near the Planck length, loop quantum gravity suggests this fabric is not smooth at all. Instead, it is woven from a network of finite, indivisible loops, a kind of cosmic mesh or spin network. Space itself has a granular, atomic structure. You cannot divide it infinitely. There is a smallest possible volume, a quantum of space. This fundamental discreteness changes everything when you rewind the cosmic movie. In the classical story, as you go backward, the universe gets smaller and smaller. The density soars toward infinity, and the equations blow up at the singularity. But in loop quantum cosmology, the universe cannot shrink past a certain point. It reaches a minimum possible volume, a smallest meaningful size. At this extreme density, the quantum nature of gravity itself becomes repulsive. Think of it like compressing a spring. You can push it down, but eventually, you hit a point where the spring's own internal structure pushes back with tremendous force. In this cosmic analogy, the spring is the fabric of space-time, and its internal structure is its quantum, granular nature. This quantum repulsion becomes so powerful that it halts the collapse completely. There is no infinite density, no point of zero volume. Instead, the equations show a graceful reversal. The contraction smoothly transitions into an expansion. The Big Bang is replaced by a big bounce. This is not a violent, classical crash, but a quantum bridge from a prior phase of contraction into our current phase of expansion. The terrifying singularity is replaced by a well-behaved, finite quantum transition. The prior universe could have been vast and old, slowly contracting over eons before reaching this quantum threshold and rebounding into what we call our Big Bang. The success of such a model is measured in two crucial ways. First, it must be internally consistent. Its mathematics must hold together without producing infinities or logical contradictions. providing a complete picture through the bounce. Second, and most importantly, it must connect to the universe we actually observe. After the bounce, the model must naturally produce a hot, dense state that then evolves, through the known laws of physics, into the cosmic microwave background, the distribution of galaxies, and all the other landmarks of our standard cosmology. Remarkably, simplified versions of loop quantum cosmology do exactly that. They show that the quantum bounce would generate conditions nearly identical to those of the standard hot Big Bang, but without the paradoxical starting point. It would also produce a specific spectrum of primordial density fluctuations, seeds for galaxies that could be distinguished, in principle, from those of inflation. The mathematics offers a clean, elegant escape from the singularity, painting a picture of a potentially eternal, cyclical cosmos connected by quantum bridges. This work represents a monumental shift in perspective. We are no longer asking what came before the bang in a temporal sense, but what lies on the other side of a quantum gravitational threshold. The answer, written in the language of loops and spins, suggests that our entire history may be one chapter in an endless story, where each universe is both an end and a beginning, linked by the fundamental grain of space itself. The mathematics of loops offers one elegant escape from the singularity, but another contender paints a reality of even greater possibility and profound mystery. This is the landscape of string theory, a vista of mind-bending scope where the question of what came before our Big Bang transforms into a cosmic selection problem. String theory, in its quest to be the theory of everything, suggests that the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating strings. The different vibrational patterns of these strings give rise to all the particles and forces we see, from electrons to photons. But this elegant idea comes with a staggering consequence: the existence of extra dimensions of space. To make the mathematics work consistently, string theory requires not just the 3 spatial dimensions we experience, but 6 or 7 more, curled up into shapes so fantastically small we never perceive them. The geometry of these hidden dimensions is not arbitrary. It determines the laws of physics in our observable 3-dimensional world, setting the values for constants like the strength of gravity or the mass of an electron. And here lies the breathtaking and perhaps troubling revelation. There is not just one way to curl up these extra dimensions. The mathematics allows for a colossal number of stable configurations, each corresponding to a different possible vacuum state for a universe, each with its own unique set of physical laws. This is the string theory landscape, a cosmic catalog of perhaps 10 to the 500 distinct possible universes. In this framework, our universe with its life-permitting constants is not a finely tuned miracle. It is simply one entry in an almost endless phone book of cosmic possibilities. So the pressing question shifts dramatically. We are no longer asking what physical process created a universe from nothing. We are asking a different, more pointed question. What process selected our particular universe with its specific set of laws from this nearly infinite landscape of possibilities? Why this vacuum and not another? This reframes our search for a before. The Big Bang, in the string landscape view, might not be the absolute beginning of everything. It could be a local event, the moment when a region of a much larger, perhaps eternal, meta-reality settled into one particular configuration of extra dimensions, crystallizing the laws we now take for granted. This transition from one vacuum state to another is a concept physicists call tunneling. Think of the landscape not as a flat map, but as a rugged, mountainous terrain. Each valley represents a stable vacuum, a possible universe with its own laws. Our universe sits in one particular valley. The process of quantum tunneling suggests that a prior state of reality could have been in a different valley, a different vacuum with entirely different physics. Through a quantum probabilistic jump, a bubble of our current vacuum could have spontaneously formed within that old one, and then expanded at the speed of light to create our entire observable cosmos. In this picture, our Big Bang is the inflationary expansion of that bubble, the moment our local piece of reality found its stable footing. The before is simply another valley in the landscape, another set of physical laws we can scarcely imagine. This idea leads to a profound, almost humbling perspective. The fundamental constants that seem so essential to our existence, the very rules of the game, may be nothing more than local geography, the accidental topography of the particular valley our bubble universe inhabits. The search for a reason behind these numbers might be as futile as searching for a deep reason why one mountain valley has a stream and another does not. It is simply the lay of the land. Yet, this vast landscape also offers a potential answer to the fine-tuning puzzle through the concept of the anthropic principle. If the landscape is real and eternally inflating, generating countless bubble universes with random physical laws, then it is no surprise we find ourselves in a bubble that allows for complex structures like stars, planets, and observers. We could not exist in the overwhelming majority of universes where the constants forbid such complexity. Our presence here is a selection effect, not evidence of design. So the string theory landscape does not provide a neat, deterministic story of our origin. Instead, it offers a cosmic lottery. Our universe's specific properties are the winning numbers, drawn from an urn containing more possibilities than atoms in our observable cosmos. The moment of our Big Bang was not the beginning of time, but the moment our lucky ticket was cashed in, initiating the local expansion of a bubble with just the right conditions for everything that followed. This transforms the singularity from a wall into a doorway, one leading not to a prior time, but to a vaster, more populous and strangely silent meta-reality where all possibilities are realized somewhere. And our story is just one paragraph in an infinite library. But this pristine cosmic canvas may not be perfectly uniform after all. When scientists stare deeply into the map of the cosmic microwave background, they find a few subtle, strange features that stubbornly refuse to fit the simplest story. These are the CMB anomalies, and they represent either tantalizing cracks in our model or the cosmic equivalent of seeing faces in the clouds. The most famous of these is nicknamed the axis of evil. It sounds dramatic, and it is. When researchers analyze the temperature fluctuations across the sky, they expect a random, symmetric distribution, like static on an old television screen. But the data reveals an unexpected alignment, a curious preference for certain patterns to line up along a particular axis in space. It is as if the universe's first light carries a faint, ghostly compass needle pointing in one specific direction. Another puzzle is the large-scale power deficit. On the very biggest scales, the size of the entire observable universe, the temperature variations are noticeably quieter, less dramatic than our best models predict. It is like listening to a symphony and realizing the deepest, lowest notes are strangely muted, missing the power you expected from the orchestra's foundation. Then there is the cold spot, a strangely large and cool region in the southern sky that seems unusually empty and difficult to explain by standard random chance. The mainstream cosmological view, held by most scientists, is one of cautious skepticism. Our universe is a single data point. When you have a map with millions of pixels, some unusual patterns are bound to appear purely by random statistical chance. Furthermore, these signals sit at the very limit of our measurement precision, where subtle foreground effects from our own Milky Way galaxy or instrumental noise could easily mimic or create such features. The scientific process requires extraordinary evidence for extraordinary claims, and so far, these anomalies have not risen to that level. They are intriguing curiosities, not paradigm-shifting discoveries. Yet, for a smaller group of researchers, these anomalies are like faint scratches on a window, hints that we might be seeing not just noise, but something beyond the glass. If these features are real cosmological signals and not illusions, they could be profound. The axis of evil, for instance, could indicate that our universe is not perfectly isotropic. It might have a preferred direction imprinted from its birth, a fossilized pointer towards something in a larger meta-reality. Perhaps our inflationary bubble formed in an asymmetric environment, or our universe is part of a cyclic process that leaves a directional memory from a prior cosmic phase. The large-scale power deficit could be a signature of a finite universe, one with a specific topology that cuts off the longest waves. Or it might be a relic from a pre-inflationary era that limited how far those primordial seeds could form. The cold spot could be a bruise, the imprint of a collision with another universe in the vast multiverse, a cosmic kiss that left a cool, empty dent in our sky. These interpretations are speculative and controversial, but they keep the question alive. They remind us that our standard model, for all its success, is built on the assumption of a simple, featureless beginning. Any persistent deviation from that simplicity is a potential clue, a whisper that the true origin story might be more complex, more textured, and perhaps connected to a reality that existed before our time began. The hunt now is not just to map the CMB with more precision, but to understand these whispers. Are they the random murmurs of a single cosmic roll of the dice? Or are they the faint, echoing words of a story that started long before our own? Faced with a sky that offers whispers but no clear shouts, scientists have turned to a powerful new kind of laboratory. They are building universes inside supercomputers. This is the frontier of computational cosmology, a discipline that allows us to test the untestable by simulating reality under different sets of rules. Since we cannot rewind time or peer beyond the cosmic horizon, we can instead ask the machines to show us what might have been. The process begins with a set of equations describing a potential pre-Big Bang scenario, perhaps a quantum bounce from loop quantum cosmology, or the gentle awakening of an emergent universe from a static seed. Researchers program these equations into vast arrays of processors, seeding their digital cosmos with the initial conditions their theory dictates. They then set the simulation running, letting the laws of physics they have encoded play out over billions of virtual years. The goal is not to create a perfect replica of our universe from scratch, but to see what kind of cosmic fingerprint each origin story leaves behind. As the simulated universe expands and cools, the code calculates how quantum fluctuations grow into virtual galaxies, and how the primordial light would look to a virtual observer. The final output is a detailed prediction, a map of what the cosmic microwave background should look like if that particular model were true. Does it produce the specific statistical patterns, the precise temperature variations, and the polarization signals that our telescopes actually see? This is where the bridge between abstract theory and concrete observation is built. A beautiful mathematical idea about a colliding brane might generate a stunning simulation, but if the resulting CMB map shows strong, concentric circles that we simply do not observe in the real sky, that model faces serious trouble. Conversely, if a simulation of a bouncing universe naturally produces a large-scale power deficit similar to the one that puzzles us, that model suddenly gains credibility, offering a possible explanation for an existing anomaly. These digital universes act as rigorous filters. They allow cosmologists to rule out entire families of theories that are mathematically possible, but observationally incompatible with the cosmos we inhabit. It is a process of elimination on a cosmic scale, narrowing the field of contenders from countless elegant speculations down to those few that could genuinely describe our reality. The simulations also help us understand what to look for next. By revealing subtle, unique signatures that different models produce, they give observationalists a target list, specific patterns or statistical quirks to hunt for in the ever more precise data from telescopes and satellites. In a quest where direct evidence may be forever out of reach, these virtual worlds become our most powerful guides, allowing us to explore the echoes of creation from the safety of a server room, searching for the digital ghost of a universe that might have been. The quiet hum of our supercomputers leads us to a deeper, more human question. All this searching for a pre-Big Bang reality is not merely a technical puzzle. It is a modern chapter in one of humanity's oldest and most profound debates. Did the universe have a true beginning, or has it always existed in some form? This question has echoed for millennia, long before telescopes or particle accelerators. Ancient philosophers pondered eternal cycles of creation and destruction, while many religious traditions spoke of a definitive moment of creation from nothing. Today, that same debate plays out in the language of mathematics and physics, with the nature of the initial singularity as the central battleground. On one side are models that suggest an eternal cosmos, the cyclic universe, the bouncing quantum cosmology, and the multiverse all paint pictures of a reality with no ultimate start, where our Big Bang is merely a local event or a recurring phase in an endless story. These frameworks offer a kind of scientific infinity, removing the need for a singular, inexplicable moment of genesis. They appeal to a sense of natural completeness, where the universe simply is, always has been, and always will be, transforming but never truly beginning. On the other side stands the stark implication of a true singularity. If our best physical laws, when traced backward, inevitably lead to a point where space, time, and the laws themselves cease to have meaning, it strongly suggests an absolute beginning. In this view, the Big Bang is not just a transition, but the ultimate origin of everything matter, energy, space, and time, from a state that, by definition, we cannot describe. This idea carries immense philosophical weight, because it immediately raises the question of causality. Our entire experience of reality is built on cause and effect. Every event has a preceding cause. So if the universe itself is an event, what was its cause? This line of thinking points toward the concept of a first cause, an uncaused cause that set everything into motion from outside the chain of physical events. For some, this aligns with theological or metaphysical ideas of a creator. For scientists, it presents a formidable challenge. Can science, which operates within the framework of natural laws and observable evidence, ever address what, if anything, triggered the universe from a state of non-existence? Many physicists argue that if time itself began at the singularity, then the question of a cause becomes meaningless, as causality requires a temporal framework of before and after. There is no before to contain a cause. Others contend that our current inability to describe that moment does not prove it was an absolute beginning, only that we lack the correct theory. This tension lies at the heart of the race. It transforms the pursuit from a purely technical endeavor into a quest with profound existential stakes. We are not just hunting for equations, but for a story that either places our cosmos within an infinite, self-sustaining tapestry, or confirms it as a singular, fragile bloom in an eternal void. The answer, if we ever find it, would reshape our understanding of our place in existence. It would tell us whether we are citizens of an eternal, cyclical cosmos, or witnesses to a one-time, irreversible flowering of reality from an unknowable source. This is the human meaning behind the hunt for ancient fossils in the light. We are searching for our own cosmic context, trying to learn if our story is one verse in an endless poem, or the first and only line ever written. This grand question draws its energy from a sprawling, multidisciplinary race. The hunt for a pre-Big Bang reality is not confined to a single department or laboratory. It is a vast, collaborative, and sometimes fiercely contentious effort that stretches across the entire scientific landscape. At the forefront are, of course, the cosmologists, the cartographers of the universe. They are the ones meticulously mapping the cosmic microwave background, measuring the acceleration of expansion, and tracing the large-scale structure of galaxies. Their work provides the raw data, the observational bedrock upon which all theories must ultimately stand or fall. But they cannot interpret that data alone. To understand the first flicker of existence, you need to understand the behavior of matter and energy at energies far beyond any particle collider. This is where the particle physicists enter the race. They bring the rulebook of the quantum world, the standard model of particle physics, and the dream of theories that unify all forces. Their models of grand unification and supersymmetry provide crucial clues about the conditions that would have prevailed in that unimaginably hot, dense primordial state. They ask what particles and forces dominated, and how those interactions could have sculpted the universe's first moments. Then there are the theorists working on the most abstract frontiers, the string theorists and loop quantum gravity researchers. They are the architects, trying to construct the new mathematics that can survive the singularity. Their tools are not telescopes, but chalkboards and supercomputers, as they work with extra dimensions, vibrating strings, and quantum spins to build a coherent picture of space-time at its most fundamental. Their work is highly speculative, often untestable with current technology, but it provides the possible doorways, the brane collisions, the quantum bounces, the holographic projections, that could define the new physics we so desperately need. This intellectual ecosystem is fueled by a constant, global exchange of ideas. Progress pulses through academic conferences where rivals debate over coffee, through the rapid-fire sharing of paper preprints online long before formal publication, and through massive international collaborations that span continents. These collaborations are not just theoretical. They are building the machines of discovery. Teams of engineers, astronomers, and physicists are constructing ever more sensitive telescopes high in the Chilean deserts, launching sophisticated satellites to map the faint whisper of the CMB, and designing colossal detectors to hunt for the elusive signature of primordial gravitational waves. The race is as much about engineering marvels as it is about theoretical brilliance. And quietly, in the background, philosophers of science and cosmology contribute a crucial perspective. They help frame the profound questions about the nature of time, causality, and the limits of scientific inquiry itself. They remind the researchers that some interpretations of their equations carry deep metaphysical weight, challenging our most basic assumptions about reality. This diverse community does not always agree. In fact, vigorous, sometimes heated disagreement is the engine of progress. A string theorist's elegant model may be dismissed by a cosmologist for lacking testable predictions. A claimed anomaly in the data might be passionately defended by one group while another attributes it to statistical noise. This tension is not a weakness, but the system's greatest strength. It ensures that ideas are stress-tested from every possible angle, that only the most robust survive, and that the path forward is carved through a relentless process of challenge and refinement. The answer to our cosmic origin will not emerge from a single brilliant mind working in isolation. It will be forged in this collective furnace of observation, theory, debate, and technological ingenuity, a testament to humanity's shared drive to understand its place in the story of everything. So where does this sprawling race actually stand today? The honest truth is that no single model has crossed the finish line. There is no scientific consensus on what, if anything, existed before our Big Bang. The frontier remains wide open, a landscape of brilliant possibilities where the most we can say for certain is where our current understanding definitively ends. That endpoint is the prevailing, pragmatic view held by the majority of working cosmologists. It is the inflationary Big Bang model, a framework of breathtaking success that describes the evolution of our universe from a fraction of a second after the singularity onward with incredible precision. Within this model, the initial singularity is treated as a fundamental boundary. It is the ultimate veil, the place where our known laws of physics cease to provide answers. For many researchers, this is not an admission of defeat, but a clear-eyed acknowledgement of a limit. Their focus is on understanding everything that happened after that boundary, building a coherent history from the first tremors of inflation to the galaxies we see today. This is the solid ground of established cosmology, a story backed by a mountain of evidence from the cosmic microwave background to the accelerating expansion of space. Yet, just beyond that solid ground, several paths are being mapped with intense seriousness. These are not wild speculations. but structured research programs pursued by some of the sharpest minds in physics. They represent the leading contenders in the race to go beyond the veil. The multiverse concept, particularly through the mechanism of eternal inflation, is one such frontrunner. It emerges naturally from the mathematics of inflationary theory itself, and offers a sweeping, if untestable, vision of our universe as one bubble in an infinite, frothing cosmic sea. While its vastness can feel philosophically daunting, it is studied as a rigorous consequence of applying quantum field theory to the earliest moments, providing a potential answer to the fine-tuning of our physical constants. Similarly, quantum bounce scenarios like those from loop quantum cosmology are grounded in ambitious attempts to formulate a theory of quantum gravity. They replace the mysterious singularity with a well-defined quantum transition, offering a mathematically clean picture of a universe that could have existed before our own in a cycle of contraction and expansion. These models make specific, testable predictions about the primordial universe that differ from standard inflation, placing them firmly in the realm of empirical science, even if the evidence remains elusive. The race is defined by this tension between the solidity of what we know and the audacity of what we might discover. It is a healthy, necessary division of labor in the scientific quest. Most of the community continues to refine the standard model, using ever better data to probe the details of inflation and the nature of dark energy. Meanwhile, a vital contingent pushes at the edges, trying to construct the new physics that could make the singularity vanish into a deeper story. This is not a conflict, but a collaboration across different levels of risk and reward. The lack of a winner is not a sign of failure. It is the exhilarating signature of a field grappling with its biggest questions. We are in a period of exploration where multiple doors stand open, each leading to a different vision of cosmic origins. The next great discovery, a twist in the cosmic microwave background, a new particle from a deep underground detector, or a breakthrough in quantum gravity mathematics, could suddenly make one of these paths glow brighter than all the others, guiding us toward a new consensus. Until that moment, the only honest answer to what came before the beginning is a thrilling and collective admission: we are still searching. The silence of the data so far is not an end, but a call to build better ears. This race is now accelerating into a new era of experimentation, where the next generation of tools is being forged with one clear mission: to listen for the faintest whispers from the other side of time. These are not incremental upgrades, but monumental leaps in sensitivity, designed to scan the cosmic canvas with a precision we have never before achieved. Their goal is to find the subtle anomalies, the statistical ghosts, or the definitive swirls in ancient light that could finally confirm or shatter our grandest theories of origin. At the forefront of this hunt are the guardians of the first light, the cosmic microwave background observers. On the ground, in the thin, dry air of the Chilean Andes, the Simons Observatory is rising. It is not a single telescope, but a suite of them, featuring tens of thousands of superconducting detectors that will map the CMB's temperature and polarization across a huge swath of the sky. Its sensitivity will be so profound that it could detect the polarization signal from a single galaxy cluster at the edge of the observable universe. This power is aimed squarely at the hunt for primordial B modes, the swirling signature of gravitational waves from the universe's birth. By measuring with such exquisite detail, it will either find that elusive signal or place such stringent limits that whole families of inflationary models and their pre-Big Bang alternatives will be ruled out. But the ground has limitations, our atmosphere being a shimmering, noisy veil. To see with perfect clarity, we must go to space. That is the promise of proposed missions like Lightbird, a satellite observatory designed with one paramount objective: to measure the polarization of the cosmic microwave background over the entire sky with unprecedented fidelity. Free from atmospheric interference, its goal is to achieve a sensitivity that could detect a primordial gravitational wave signal 100 times fainter than any current experiment could hope to see. Lightbird would essentially take a perfect, ultra-high-resolution portrait of the universe's first light, searching for the tiny, swirly patterns that are the holy grail of cosmology. A detection would be a direct message from the first trillionth of a second, potentially revealing whether the universe's birth was a smooth quantum process or a more violent collisional event. Yet light is not the only messenger. The future also belongs to listening for the ripples in space-time itself. On the ground, the existing network of detectors like LIGO and Virgo will be joined by more sensitive facilities, hunting for gravitational waves from the mergers of black holes and neutron stars. While these are recent cosmic events, understanding the population and behavior of these objects helps us refine our models of the universe's evolution, tightening the constraints on any theory of its beginning. But the truly revolutionary step will be taken in space. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will open an entirely new window on the cosmos. Consisting of 3 spacecraft flying in a giant triangular formation millions of kilometers apart, LISA will detect gravitational waves at frequencies too low for any ground-based instrument. It will hear the mergers of supermassive black holes, the gentle spirals of white dwarfs, and possibly, just possibly, a stochastic background of gravitational waves from the very early universe. This cosmic hum, a faint rumble from the first moments, could carry information from epochs even before the cosmic microwave background was released. It is another channel, another frequency on which the universe's origin story might be broadcasting. Together, these next-generation tools form a coordinated assault on the mystery. The Simons Observatory and Lightbird will scrutinize the ancient light for imprints. LISA and its successors will listen for the primordial tremors in space-time. Each instrument acts as a filter, sifting through the cosmic noise for a signal that does not belong to the standard story. A single, clear detection from any one of them, a specific pattern in the polarization, a confirmed anomaly in the large-scale structure, or a primordial hum of gravitational waves, could instantly elevate one theoretical doorway from fascinating speculation to the leading framework for reality. They are the bridges we are building to cross the horizon of our ignorance, not with philosophy, but with photons, lasers, and the relentless, precise language of data. Ultimately, this entire race converges on a single, monumental dream. The quest to see beyond the Big Bang is not a search for one more piece of data, but for a new dictionary, a complete language of reality. This is the pursuit of a theory of everything, the final unification of all physical laws. The answer to what came before may not be a specific event we can name, but a fundamental shift in our understanding of what before even means, a shift that only such a theory can provide. Our current predicament is a story told in 2 conflicting languages. Quantum mechanics narrates the world of the impossibly small with breathtaking accuracy, while general relativity describes the cosmos of planets and black holes with equal brilliance. Yet when we try to combine their grammars to describe the universe's first instant, the story collapses into gibberish. The singularity is that grammatical breakdown. It is not a place or a time, but a screaming error message in our mathematics, telling us our description is incomplete. A true theory of everything would be the seamless fusion of these 2 rulebooks. It would provide a single, coherent set of equations that work from the scale of a subatomic particle to the expanse of the entire cosmos, without breaking down at any point. In such a framework, the terrifying infinity of the classical Big Bang singularity would simply not appear. It would be smoothed away, replaced by a well-behaved finite transition. Whether this final theory takes the form of string theory with its vibrating strings and extra dimensions, loop quantum gravity with its fabric of woven spacetime, or some yet undiscovered idea, its power would be revolutionary. It would give us the vocabulary to talk about the universe at its very inception. We could ask questions that are currently meaningless. We could describe the state that led to our expanding cosmos, not as a before in time, but as a different configuration in a more fundamental reality. Think of it like the transition between water and ice. To a creature that only understands liquid water, the moment of freezing seems like a singular, catastrophic event where its world solidifies inexplicably. But with a deeper understanding of physics and molecular bonds, we see freezing not as a wall, but as a phase change, a smooth transition governed by temperature and pressure. A theory of everything aims to provide that deeper understanding for the cosmos. It would recast the Big Bang from a mysterious beginning into a phase change within a grander, perhaps timeless, structure. This is why the search for a pre-Big Bang reality is inseparable from the quest for quantum gravity. Every contender, the cyclic bounce, the colliding branes, the emergent universe, is a tentative sentence written in a language we are still inventing. They are predictions of what a complete theory might say about our origins. The ultimate answer, therefore, may not be a dramatic story of a prior universe. It might be a profound, elegant equation that shows how a universe like ours naturally arises, with no need for a starting point at all. In that equation, the concepts of beginning and before might dissolve, revealing a reality where existence is its own prerequisite. Until we hold that equation in our hands, the veil remains. But the dream of lifting it, of reading the first page of the cosmic story in a language that makes perfect sense, is what drives the entire race forward. That final equation might not describe a beginning at all, but an eternal reality. The possibility that the universe, in some form, has always existed is not a retreat into mystery, but a profound conclusion some of our deepest theories point toward. This idea of an eternal cosmos forces us to redefine what forever even means. We are not talking about an infinite timeline stretching backward in a straight line, like a movie that started at negative infinity and is still playing. Our classical intuition about time breaks down completely at the extremes we are discussing. Instead, eternity in a quantum gravitational context could be something far stranger, and perhaps more beautiful. It could mean a state beyond time, or an endless cycle where beginnings and endings are merely phases in an everlasting transformation. Consider the concept of timelessness. In some approaches to quantum gravity, time is not a fundamental ingredient of reality. It is an emergent property, a useful illusion that arises from the relationships between things, much like temperature emerges from the jostling of molecules. In this view, the true foundation of the cosmos is a static, unchanging network of relationships, a kind of cosmic blueprint. What we experience as the flow of time, from the Big Bang to the present day, is this frozen structure being read in a particular sequence. From this perspective, asking what happened before the Big Bang is like asking what is north of the North Pole on a globe. The question assumes a framework that does not apply to the fundamental shape. The universe just is in a complete, timeless configuration. Our journey from past to future is us tracing a path through an eternal, pre-existing landscape. The other face of eternity is not stillness, but endless rhythm. This is the vision of the cyclic or bouncing universe models we have explored. Here, eternity is not a frozen picture, but an infinite dance. Each cycle, a long period of expansion, perhaps a contraction, and a rebirth lasts for trillions of years. But the process itself has no start and no finish. Our Big Bang was not the first note of the symphony. It was simply the latest movement, preceded by an endless number of prior universes, and destined to be followed by an endless number of future ones. In this framework, creation is not a singular event that happened once. It is an ongoing, perpetual process, as natural and unceasing as the waves on a shore. Each universe forgets its predecessor in the fiery reset of the bounce or the transition, but the grand cycle itself is eternal. This represents a monumental shift in our cosmic story. For decades, the dominant narrative has been one of a singular creation event, a definitive moment when everything began. An eternal model replaces that with a narrative of transformation. The mystery of the first cause dissolves because there is no first cause to find. The universe does not need a reason to start existing, because in a fundamental sense it never started. It has always been here, either in a timeless state or in an endless cycle of renewal. This does not make the universe any less wondrous, but it changes the nature of the wonder. Instead of marveling at a one-time miracle, we marvel at an infinite process, a reality capable of perpetually reinventing itself according to its own internal, logical rules. Such a resolution carries a deep, almost philosophical satisfaction. It aligns with a principle often sought in science, that of a self-contained, self-explaining reality. An eternal universe requires no external primer, no outside hand to wind it up. It is its own reason for being. The low entropy starting point that gave us time's arrow is no longer a bizarre, fine-tuned initial condition, but a natural product of each cycle's reset mechanism. The laws of physics are not arbitrarily set at the moment of creation, but are perhaps the only stable, self-consistent possibilities within the eternal structure. This vision offers a different kind of answer, one that feels less like finding a starting line and more like understanding the nature of the track itself, a track that forms a loop, or perhaps has no start or finish at all. Yet, this eternal answer is not a simple escape from the mystery. It simply moves the profound questions to a different plane. Instead of asking what caused the universe, we must ask why the eternal structure exists in this particular, life-permitting form. Why does the timeless blueprint or the cyclic process yield a universe with stars, planets, and conscious observers? The quest for understanding continues, but its focus shifts from a hunt for a first moment to a deeper exploration of necessity and possibility within an everlasting reality. The silence from beyond the cosmic horizon might then be the quiet hum of eternity itself, a background of existence that has no beginning because it is the very fabric from which beginnings are woven. The very tools that let us ask this question may also define its limits. There is a humbling possibility at the heart of the race, that the question of what came before our Big Bang might be fundamentally unanswerable by the methods of empirical science. Our entire approach to understanding the cosmos is built on a powerful assumption known as the cosmological principle. It states that, on large scales, the universe is both homogeneous and isotropic. It looks roughly the same in every direction and from every location. This principle is not a guess. It is a cornerstone validated by the smooth glow of the cosmic microwave background and the uniform distribution of galaxies. It allows us to extrapolate, to take the laws of physics we measure here and now and apply them confidently to distant stars and ancient times. But this principle is a rule we have deduced from within our universe. It is a description of the stage once the play has already begun. The monumental leap comes when we try to apply this same logic to the universe as a whole, to the meta-reality that may have spawned our cosmic bubble. Can we assume that the principles governing our observable patch apply to the totality of existence, to whatever realm existed before space and time as we know them crystallized? This is not a small step. It is a leap into a logical abyss. We are attempting to use the rules of the game to describe the factory that manufactured the game board and the dice. It might work, but it is just as likely that the framework of causality, of before and after, of even the concept of a state that can be observed, breaks down entirely outside our particular bubble of reality. This leads to a sobering frontier for many of the most elegant theories. Concepts like the string theory landscape or the eternal multiverse are breathtaking mathematical structures. They can offer self-consistent, beautiful narratives for how a universe like ours could arise. Yet, if the other bubbles or vacuum states are forever beyond our cosmic horizon, causally disconnected from us, then those theories may reside permanently in the realm of profound speculation. They could be true in a mathematical sense, yet fundamentally untestable by any observation we could ever make from inside this universe. This does not make them worthless, far from it. They expand the landscape of logical possibility and push our understanding of quantum gravity. But it does place them in a different category from a theory that makes a clear, falsifiable prediction about the cosmic microwave background. Acknowledging this boundary is not a surrender, It is a crucial part of the scientific race. Knowing the limits of what can be known is itself a form of deep understanding. It forces a rigorous honesty. It asks us to distinguish between what we can compellingly infer from evidence and what we can elegantly imagine from equations. The search does not stop at this edge, but it changes character. It becomes a partnership between hard empirical science and deep philosophical inquiry, each informing the other about the nature of reality, knowledge, and the profound mystery of why there is something rather than nothing. The ultimate answer may not be a date on a cosmic calendar, but a clearer view of the horizon line where our light ends and the great unknown begins. The singularity was a wall, but every wall invites us to find a door. Our journey began with the stunning success of the Big Bang model, only to watch its own equations dissolve into infinities at the very moment they promised to explain everything. That breakdown was not a failure but a beacon, signaling a deeper reality waiting to be understood. From that point, the race exploded outward into a universe of possibilities. We have explored cosmic inflation, which smooths the early universe but may also erase its past. We have confronted the chasm between quantum mechanics and gravity, the fundamental rift that makes the singularity inevitable in our current physics. And in trying to bridge that chasm, we have encountered breathtaking doorways. The cyclic bounce of a quantum universe, the gentle awakening from a timeless seed, the violent kiss of colliding branes in a hidden dimensional sea, and the infinite bubbles of a multiverse where our entire history is just one local event. Each is a different answer to the same profound puzzle, a different sketch of what the parent theory of everything might look like. This race was never about finding a simple date on a cosmic calendar, a tidy before to inscribe in a textbook. It is a struggle for a coherent framework, a set of rules so complete that the question of a beginning transforms or simply fades away. The goal is a story that makes sense of why we are here in a universe with time, with stars, and with laws that allow for questions to be asked. In that relentless pursuit, even without a definitive winner, we have already won a deeper kind of understanding. Our concepts of space and time have been stretched and reshaped. We now speak seriously of extra dimensions, of a granular quantum spacetime, of a cosmos where the laws of physics might be local and accidental. The very nature of scientific inquiry has expanded to wrestle with questions that hover on the edge of philosophy. We have learned that some answers might be forever beyond our cosmic horizon, and that the silence of the data is as instructive as a shout. The next decade will be decisive. New eyes on the sky, from observatories like the Simons Array to space missions like Lightbird, will map the ancient light with unimaginable precision. Gravitational wave detectors in space will listen for the faintest hum from the first moments. These are not just better telescopes. They are time machines, built to decode whispers from the other side of the singularity. They may find the swirling signature of primordial gravitational waves, or a statistical anomaly in the galaxy clusters that breaks the standard mold. One clear signal could suddenly make a single theoretical path glow with the light of evidence, guiding us toward a new consensus. Until then, the landscape remains open, a testament to human curiosity. So we leave you with this question, not as a conclusion but as an invitation. Look at the contenders we have walked through. The eternal cycle, the quantum bounce, the multiverse bubble, the holographic projection. Which vision of cosmic origins feels most compelling to you? Which doorway do you find yourself drawn to, not as a definitive truth, but as the next chapter in this greatest of all mysteries? Your curiosity is part of the race too.